Alright, so I've got a very ambitious goal for this video, and it's probably going to be rather long. And what I want to do is I want to give you an overview of the standard distribution. So standard distribution is right there. And basically the question that I want to ask is, where does this table come from? And where does this table come from, and how is it generated, and what does calculus have to do with that? That's kind of the ultimate question that I'm going to get to by the end of this video, but I'm going to hit a lot of things along the way. So the standard distribution is something that you're going to probably see somewhat when you're talking about probability and a statistics unit in pre-calculus. This video is prompted by the fact that I'm looking at my calculus curriculum and they sort of talk about it in calculus. Certainly you're going to be talking about it in stats, but your stats course may use calculus, or it may be a stats course designed for people who haven't done calculus. So if you're watching this, there's probably going to be parts of this that are going to be too easy for you and probably things that you haven't learned yet. My goal is to sort of give an arcing trajectory over the whole sort of subject and not really filling in the details, but just giving an overview. So hopefully by the time you've finished watching this video, you've got a little bit bigger view of the landscape, and then you can start to fill in some of the details. And then, just like anything else, I can't show you what's really beyond the horizon, so the more math you take, the more you'll learn about what I'm talking about. Okay, so where does this start? Well, I'm going to start by flipping 10 coins. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 coins. And what I'm going to do is I'm going to flip them. And I'm going to count how many heads that I've got. And so I'm going to go 1, 2, 3, 4, 5, 6, 7 heads. Okay? Then I'm going to do it again. And I'm going to get 1, 2, 3, 4, 5, 6 heads. I'm going to do it one more time. And I'm going to get 1, 2, 3, 4, 5, 6, 7 heads again. Okay, so I've just done it 3 times. What I really want to be interested in is what would happen, what would I get as results if I did it 100 times? How about if I did it 2,048 times? Well, I'm not actually going to flip these 100 times, and I'm not going to flip them 2,048 times, but we're going to go to my spreadsheet, and the spreadsheet is going to give us a simulation that's sort of related to that. Okay, so here's my 10 coin toss spreadsheet. And basically what have I done here? Well, what I did is in each cell, I just told it to assign a random number to each cell. And so I've got A, B, C, D, E, F, G, H, I, J. Those are my 10 coins. And I just basically, if I hit enter, it gives me new random numbers, or it should give me new random numbers. If I just sort of throw something in here, it's going to recalculate everything. So every single time I just sort of hit a random number, it recalculates everything. So I'm sort of tossing coins every time. I'm not putting any specific number in there. All I'm doing is, if I just put a number in there and hit enter, it recalculates everything. So it sort of retosses the coins. And then here, I've got a little count if function. So I'm counting if the cells A1 through J1 are less than 0.5. So that's what I'm going to call heads. So this is basically counting the number of heads that I've got. And so I can just sort of flip as many times as I want. Every time I'm flipping, it's just counting, it's sort of doing theoretical flips and counting how many of those come up in quotes heads. And then, because the spreadsheet doesn't care, I've done this 2048 times. Why 2048 times? Well, that will become clear a little bit later in the video. And so then I've got another COUNTIF function. And so here's what I'm doing is I'm counting if the row K, how many cells in row K have a 0? In other words, how many times did I come up with no heads whatsoever? Then how many times did I count one head? How many times did I count two heads? How many times did I count three heads? All the way up. So this is basically counting in column K how many heads I came up in my simulation. Then I've got my theoretical prediction. And my theoretical prediction is based off of Pascal's triangle. So I think I'm going to just take a second and stop this video and go over and review Pascal's triangle and binomial theorem, and we'll be back here in 1 second. Okay, so we're back here, and Pascal's triangle goes a little bit like this. And you should have seen it already. I'm not going to go into it in big detail. Basically what I'm doing is I'm starting with a 1 and a 1, 1, and then I add these, then I continue ones down the outsides like this, and then on the interior I do this plus this equals 2, this plus that equals 3, that plus that equals, so 1 plus 2 equals 3, 2 plus 1 equals 3, 1 plus 3 equals 4, 3 plus 3 equals 6, 3 plus 1 equals 4, and then I continue down like that. I'm not going to go into Pascal's triangle. Okay, and so then basically where that comes into binomial theorem or probability, I'm going to just give it for probability, that I'm going to get this thing NCR times the probability to the n minus r times 1 minus the probability for the r. I'm probably getting those mixed up. I'm going a little bit fast. So what does all this mean? So I've got a coin. So for a coin, the heads probability is 1/2. The probability of getting heads is 1/2. And so the probability of not getting heads is symmetrical. I'm starting this easy. So my probability of each outcome is going to be NCR 1/2 to the 10th in my case. So going fast, I got 10 coins, and so the probability of each outcome is going to be given by this. And so what is this NCR? NCR is my coefficient out front, and you guys have seen this before, hopefully. So it's going to be n factorial over n minus r factorial, also over r factorial. Okay, so if I go, what is the probability that if I take 10 coins, I'm going to come up with exactly 5 heads? Well, the probability that I'm going to, well, or how many different ways? How many different ways can I throw 10 coins and come up with 5 heads? Well, I'm going to go 10 factorial over 5 factorial over 5 factorial. And so I'm going to go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 over 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. And so that's 10 factorial over 5 factorial, 5 factorial. Those cancel out. That cancels out that. And that going fast. And so I end up with 9 times 4 times 7, which is going to be 36 times 7, which is going to be, that's 42, and that's 21, so I'm going to get 252. So I have 252 ways of coming up 5 heads. Okay, back to the spreadsheet. Alright, so I'm back to my spreadsheet, and right here, this is my little Pascal's triangle thing here, where what I did is I did, I think I just plugged the numbers in. I didn't come up with a formula for it. But you'll see that here's the number of heads, 5 heads. I threw coins 10 times. I did 10 coins, and the probability and the number of different ways that I can have 10 coins come up 5 heads is 252, just like I showed you in the previous little segment. And so if I do have Pascal's triangle, I've got 1, 10, 45, 120, 210, 252, blah, blah, blah. And it comes up with the total number of ways that I can the total different combinations I can have of heads and tails is, there's basically like 124 different ways that those coins can come up. So why did I throw, why in my spreadsheet am I choosing 2048? Well, just because it's twice that. So if I went off of Pascal's triangle is just a theory about how things should work. So if I just go off of Pascal's triangle, then if I threw the coin 2048 times, then I would expect that I would get 2 times no heads, 20 times I'd get 1 head, 504 times I'd get 5 heads, 90 times I'd get 8 heads. And then in this column, I have the actual results of the experiment. So instead of 2, which was expected, I got 1. Instead of 20, what I got was 19. Instead of 90, what I got was 99. Okay, so then I have a little chart here, if I can pull it up. And in the chart, I've got my theoretical, which is going to stay the same, and here I've got my experimental. And what I can do is I can actually, all I got to do is just put a dummy cell in here, and it's going to recalculate everything. So every time I sort of hit enter, it's kind of jumping around in a way that I don't want it to. Let's try it up here. Every time I hit enter, the experimental distribution changes, but the theoretical distribution stays the same. Okay? So you can see what's happening. If I every single time I do this, I'm throwing theoretically 20,480 coins in groups of 10 and seeing what and plotting what the result is. How many heads, how many tails, etc., etc., and comparing against the theoretical. Then, as just sort of a sidelight, I want to stop this video, and then I want to come back and show you what would happen if I only did it for a sample size of 100. So if I threw 1,000 coins in 100 groups of 10. Okay, so now instead of having 2,048 coins, I now have, or instead of having 20,480 coins, broken up into 2,048 groups of 10, I now have 1,000 theoretical coins broken up into 100 groups of 10. And so what this is telling me is, so now I'm just only counting if K1 through K100 equals this number. And so then here's my theoretical probability where I've just taken Pascal's triangle and I've multiplied it by 100 and divided it by 1024 to get the theoretical for what I should get for my experimental for just 100 samples. And so then you can see what's going to happen here is I move this around. So as I take repeated samples, you're going to see that the blue lines, which are the experimental, kind of look like the red, kind of look like the orange line. But because my sample size is so much smaller, there's going to be a lot of difference between the individual samples and the theoretical results. So if I just kept doing this forever and ever and ever, and I averaged out the blue, I would eventually get the orange. But each individual blue is going to have kind of roughly the characteristic shape of the orange, but there can be some pretty substantial differences. And then once again, if I go back to my much larger sample size, that holds true. There are always going to be differences between the experimental line and the theoretical line, but for larger sample sizes, those differences are going to be a lot smaller. Okay, so then this brings us up. You can sort of see that this is sort of our normal distribution. So this kind of looks like the normal distribution. Here I've got the Wikipedia article on normal distribution, and this red line right here kind of looks vaguely similar to this blue and orange line right here. So there's got to be some sort of connection between them. But now we sort of experimentally determine this with Pascal's triangle or binomial theorem or experimentally or whatever. And this to me looks like this is some kind of smooth function. So I really want to know what that smooth function is. So next we're going to look at what that smooth function, what function generates this curve. Okay, so that was one of the questions that I came up with, was what function generates that nice sort of normal distribution curve. So here we've got some normal distribution curves, and then here, well, you do a little bit of work and you sort of see that they come up with y equals e to the negative parentheses x minus a squared divided by b, gives you kind of that nice curve. But then let's figure out some things about that curve and kind of learn some more about this function. And this is where we're going to start. And so then we're going to blend some calculus and algebra. So over here in a font probably too small for you guys to see on the YouTube video, I can change what a and b is equal to. So right now a equals 1. So the question you should ask yourself is, what's going to happen if I change a to 2? Well, it moves the center point from 1 to 2. If I change it to 3, it moves it over to 3. So a gives us our horizontal shift. So let's change it to 0. What's b going to do? If I make b 2, what's going to happen? Well, maybe it was hard to see. I see what's happening. As I make b larger, it flattens out. If I make b less than 1, it's going to get more narrow. So b is going to determine kind of the width of my function, or the horizontal stretch. So b in this case is the horizontal stretch, and a is going to be the horizontal shift. Okay, so this is the graph that I wanted to look at next. And so basically this is also from Wikipedia, And this is your sort of your standard, your normal distribution. And then here you've got these things, mu, 1 sigma, 2 sigma, 3 sigma. And so mu is the mean, and then sigma is the standard deviation. And you sort of look and you go, well, okay, I can sort of see that the mean is kind of at the highest point. But then where does this standard deviation come from? How do I find this standard deviation other than just sort of, well, there's two answers to that. And there's the algebraic experimental answer, and then there's sort of the calculus answer. And so what I really want to say as we sort of get into this is that the mean is where the first derivative, let me get back to this, and let's zoom in a little bit. The mean is going to be where this function has a first derivative equal to 0, and the standard deviation is going to be somewhere in here where the second derivative of this function is equal to 0. So we're going to get there eventually. And I think that what I want to do now is I want to sort of take a little bit more data, and then I want to graph that and pull some things in, tie experimental and theoretical together, and then start introducing the calculus. Okay, so experimental data to work on normal distribution. I've got all these little beakers, and I'm not sure if the masses are normally distributed, but we're going to assume that they are. And we're going to just sort of weigh 12 of them and just see what we get by plugging it into my little graphing calculator, using a lot of different technology here. And it's going to give us our number. And I'm not going to bore you with the details, so I'll do one more. And then we're going to pause the video. Okay, and so I got my last beaker, and it says 29.18, and so I enter in 29.18. And then I hit stats, and I do calc, and I do one variable stats on list 2. And here I've got my mean is 29.03, and my standard deviation is 0.124 down here. And so then we'll sort of just talk briefly about what those mean. So then sort of algebraic stats, mean is just kind of, that's the average, which basically means so the calculator was basically just adding up all 12 masses and then dividing by 12, and that's what I got as my mean, which was 29.03. Okay, standard deviation, just giving you an overview, standard deviation is the form sigma is equal to square root of the sum of x minus the mean squared over n. Okay, so that's a lot of different things in there. So basically what it's saying is procedure find the mean. Find the mean, subtract the mean from each data point, square that. Add them all together. Okay, find the mean, subtract the mean from each data point, square that result, add all of your results together, divide by the total number of data points, take the square root. So find the mean, data points minus the mean, square it, sum them all together, divide by the total number of data points, take the square root. There's your standard deviation. But what is this going to mean in terms of our normal distribution? So if I've got my normal distribution, well, what I was saying is that this, so if this is y equals e to the negative x minus a squared over b, I'm saying that this point, the mean is where y prime y prime equals 0, and this is my sigma right here. Sigma is where y double prime is equal to 0. Okay, so let's look at this function, and let's take its derivative, and let's take its second derivative. Well, so y prime, this is a chain rule product rule, or this is just a chain rule. So I'm just going to go pretty fast because we're doing that in this video. I'm going to have an e to the negative x minus a squared over b. And I'm going to have the derivative of this out front, and that's going to be negative 2 over b parentheses x minus a. And so I want to know, where does this function equal 0? Well, b is a constant, so negative 2 over b, that's still a constant. My exponential function can never get to 0. It's asymptotic towards 0, but it never gets to 0. So the only thing that it can equal 0 is this. So when x minus a is equal to 0, y prime is equal to 0. Well, where does that happen? Where x equals a. Well, what we said is that this function has a derivative of 0 at the mean. So what that's telling me is that the mean is equal to a in this equation. So we've learned something here, that a is the mean. Okay, well, let's keep going. Let's find the second derivative. Well, second derivative is going to be a little bit tricky. This is going to be a chain rule product rule problem. And things are going to get messy, but we'll hang with it. Okay? So, chain rule product rule, I'm going to take this and I'm going to take that and put it there. Then I'm going to take the derivative of this and put it in there, and the derivative of that is just going to be minus 2 over b. And the derivative of this, well, I've already found the derivative of that. that stuff that's going to get wiped out on YouTube. X minus a squared over b. Okay, so now if I sort of, and now I want to set that equal to 0. And again, I'm going through this really, really quickly. This exponential function and this exponential function, they can never equal 0, so I don't even really need to consider them. Here I've got a minus 2b in here, and I've got a minus 2b in there. So I'm going to replace this with a 1. I'm going to replace that with a 1. And so I'm going to get this. So after I've simplified down extremely quickly, I'm going to get that negative 2 over b x minus a squared plus 1 is equal to 0. So I'm going to say x minus a squared is equal to, switch that around, b over 2 should be. That's what I got. And so then we're going to get x minus a is equal to square root of b over 2. Now, here's my x. Here's my a. So this is x minus a. So my standard deviation from the mean out to the point of inflection is going to be x minus a. So I'm going to say that my sigma is equal to the square root of b over 2, or I could say that I could switch that around and say that b is equal to 2 sigma squared. Okay, so then, just this is a long section in the video, I'm going to rewrite this as e to the negative x minus mu squared over 2 sigma squared, and I'm going to rewrite it as y equals e to the negative 1/2 x minus mu over sigma squared, and then just go on Wikipedia if you want to know more about this. I'm going to throw a factor out front, and that factor is going to, this is what's going to make it a normal distribution. So this is going to mean that the area under the curve is always 1, and that's, we're going to have to talk about integration here in a little bit. So then if you look on Wikipedia, this is the function that they give you as this is the normal distribution function, and this is sort of how we've gone through it. Okay, so I'm back to the graphing calculator, and now what we're going to do is we're going to just sort of build up, the function that's going to give you the normal distribution for my beaker data. So I've got this 1 divided by sigma, and my sigma is 0.124, times the square root of 2 times pi to the 1/2. That's my constant out front. And then I've got e to the big parentheses, so it's minus 1/2 times x minus my mean, and my mean is going to be 29.03. And all of that is going to be divided by my sigma, which is 0.124. And then I've got to square that. And that messy function should give me right over there the normal distribution for my data on my beakers. So I would expect that the average beaker is going to have a mean, the average beaker is going to have a mass of 29.03, and that we're going to have some of them, and that basically they're all going to fall between 28.5 and 29.5 is going to be the mass range for my beakers. But so then we have to come into, like, we got to get back to this. So the other thing that you learn is you go, oh, well, 34.1% of your data should be between one mean and one standard deviation. And then 13.6% of your data should be between one standard deviation and two standard deviations. And then 2.1 between 2 and 3. But where do these numbers come from? How do they get these numbers? So I figured out where the mean is. The mean is going to be where the first derivative of this function equals 0. That's where the mean's going to be, and that's going to be right there. And I also figured out that the standard deviation is going to be where this function has a point of inflection. But where do they come up with these values? Well, these values are areas under the curve, and areas under the curve have to do with integration. Okay, so if we so then let's just take a pause and we'll set this up, and I'll show you how we can integrate this function to get these numbers. Okay, so we're back to my graphing calculator, and what I've done is I'm sort of graphing my normal distribution function, and the first thing you're going to notice is that my function, if you sort of graph it on the same set of axes, so 0, 1, 2, 3, and 0.4, you're going to see that it's a lot shorter than it appears in the pictures. And so here's my normal distribution, and I've made some simplifications, and the simplifications that I've made is I've made the mean 0, and I've made my standard deviation 1. And so by making the mean 0 and the standard deviation 1, then I've sort of simplified it down to 1 over 2 pi, 1 over the square root of 2 pi e to the negative x squared divided by 2. And so I've got the red line is showing me the whole curve, and then the pink line is showing me the sort of the area under the curve. And so I can change that to sort of be any block that I want. Okay, so the question is, where do they get off saying that this region right here is 34.1% of the data? Well, I sort of go over here and I go, if I go from 0 to 1, then, okay, so then my total area is 100% of the data. This pink area has got to be 34.1% of the data, but how do I prove that? Well, what I need to do is I need to integrate this function. So this function needs to be integrated, and it kind of doesn't look all that awful, but it is awful, and there's really essentially no way that you can integrate it without using numerical methods. But fortunately, my graphing calculator has a way to numerically integrate, and your graphing calculator probably also has a way to numerically integrate. And so I take it and I integrate it from 0 to 1, and I integrate that function numerically from 0 to 1, and I get 34.1, or I get 0.341, which is 34.1%. If I integrate it from negative 5,000 to 5,000, I get a strange number. I don't think it likes me to do that. That's better. Okay, so if I go from -5 to 5, I get basically 1. And then the numerical simulation gets sort of messed up. If I sort of go out too far, it gets messed up. Okay, so let's think about some other things. If I say that from -2 standard deviations below up to 1 standard deviation above, that should be 13.6 plus 34.1 plus 34.1. That should be 81.8% of the data. So if I go from -2 to +1, I get 81.8% of the data. And I do that there. And basically, so the pink is going to be 81.8% of the total under the curve. Okay, so then we're going to come back and we're going to look at my beaker data one more time, and then we're basically done. Okay, so I've got my beaker data, and my beaker data has a mean of 29.03, and it's got a standard deviation of 0.124. And so if I plug that into my normal distribution formula, this is the formula that I come up with. And suppose that I wanted to ask the question of how many beakers would I expect to be between, say, 28.9 grams and 29.1 grams. So less than or equal to 29.9 grams or 29.1 grams. Now let's assume that my scale is going to round. So let's say 29.90. That's fine. So I'm going to get 28.90 grams or 29.10 grams. And so that's about how many I would expect. And I could go to my z-tables and I could sort of figure out how many standard deviations below 2903 that is, and how many standard deviations it is above 2903. And I could find that all in my z-table. But sort of the point of math is that we don't want to go running to tables if we don't have to. And so, since we can numerically integrate now, I can just take the integral, and we're going to do the integral from 28.9 to 29.1 of this messy function, and it doesn't matter because we're just plugging into the calculator and the calculator can do it for us, and we come up with 56.7%. So I would expect that 57% of my beakers would fall between 28.9 grams and 29.1 grams. Okay. So that's tied a whole lot of things together, from binomial distribution and Pascal's triangle, and probability of coming up with 5 heads if you throw a coin. If you throw 10 coins, how many times will you come up with 5 heads, etc., etc., using calculus to understand, and then using calculus to understand that for this little graph, the mean is where the first derivative of that function equals 0. The inflection point is where the second derivative equals 0. And the area under the curve should equal 1. And if you want to figure out how many of your data points are going to fall between a certain region of your numbers, you take the integral of that numerically from the end of your beginning of your region to the end of your region, and it tells you what percentage is going to be in that region. And so that is done.